through with file systems, we'll go ahead and jump into review. And what time is our exam next week? 8. Right? It is not at 8:15. Your exam will run from 8 a.m. to 9:50, and that's where it will end. You're free to show up anytime between those two extremes, or maybe even early for the exam. I'm usually here early and I answer questions before the exam. Okay. So, last time we were talking about journaling file systems. And what was the advantage of the journaling file system? What do you guys think are some of the big advantages of the journaling file system over, say, the Berkeley fast file system?
Really fast recovery.
We have really fast recovery. Yes, that's one of them.
Frees up the CPU a lot, right? Or for the...
I know where you're going, and that's the right answer.
It passes off the I/O
Yeah, so what we're doing now,
quickly. Yeah.
so this is the really, really big one right here. Okay. It writes the journal contiguously on disk, so it has the least amount of delay in playing out the buffer cache. So it has the least latency for I/O compared to the fast file system. This fast file system has to wait for all those random seeks to occur, whereas a journaling file system writes the journal to disk and then tells the disk itself to play out the journal while it goes off and does something else. We get that parallelism out of it. Okay. So the key parts of that is that we write to the journal contiguously to disk, which gives us the lowest latency for writing from memory to disk. Then in parallel, we have the disk controller play out the journal so the CPU can go and continue to service IOs for programs.
The disk has to support the journal, right?
Yes, the disk has to support the journal. And typically we can give the modern controllers are general purpose enough what we prefer them. It's a raise. Any questions about that? Okay, what's the as long as we're here, what's the big problem with buffer caches?
Is it that the disk and the cache can get out of sync?
Yeah, the disk and the cache can get out of sync, and that's because its major benefit, which is that it aggregates writes, has more writes in memory for a longer period of time, right? And so if we have a crash before the buffer cache is written out, we lose all of those writes. Okay, and that's why we put a maximum time on it, anywhere from 5 to 30 seconds. We don't just say, just keep going till you fill the log, because that could take days. So we have a bigger number of write operations we could lose in the buffer cache, but we use it anyway. Why?
Because it seems to be fast.
Because it seems to be fast. That's part of it.
Modern systems don't crash as much.
Modern systems are more reliable. See, it has nothing to do with computer science. That particular answer. You want to, in a computer science class, you want all your answers to have to do with how great computer science is. And this one is how great our friends in materials science, and electrical engineering, and mechanical engineering are. Okay. I don't ever put that one on the exam because I don't want any writing, treating them nicely. Okay, so we're going to finish off with the log structured file system. In the log structured file system, we take that concept of a journal and we rename it a log. Okay. The journaling file system, we used to call those logs, and then the log structured file system came along and we got confused. So the logs in the journaling file system became journals, and then the log structured file system got to keep the name log. Confused enough? Okay. It was a fun time in the 80s. Now, log structure file system is going to address the edge case for performance in the journaling file system. And what was that edge case? Anybody remember? It has to do with filling up the in-memory journal really fast. If we fill it up too fast, what's our risk? How about the risk that we haven't finished playing out the journal on disk? And then we're stuck waiting for all those random IOs again, aren't we? Okay? So what we want to do now is address the replay problem. Okay? It doesn't occur much, but it can occur. So we're just going to address it. And as in any optimization problem, the best way to optimize the replay is to do what?
Focus on the slow parts.
Focus on the slow parts, okay, which is the replay of the journal, which is the entire process. Why don't we just get rid of it? Why don't we just get rid of replay? That would reduce the amount of time it takes to replay, wouldn't it? Now the question is, how are we going to do that? Okay, so now we need to think a little bit more about what's on the disk. There's data blocks and meta information. The big problem with all the file systems we've seen so far is that even with the Berkeley Fast File System, our meta information is stored relatively far from our data blocks. Okay. What if we could store them right next to each other? What if we could store them right next to each other? We'll store the inodes and the inode map and the data map next to the data blocks. How's that sound? Okay, so I have a question for you. How do we find an inode? We saw how we did it before. It was a simple calculation, wasn't it? How are we going to find it? Okay. How many of you, did anybody have a chance to read that section? The solution is to give our metadata, one more level of indirection. That's the solution in most hard computer science problems. One more level of indirection. So what we're going to do is we're going to have metadata about our metadata. All right? So what we're going to do here on our logs is when we write data, remember that data is just going to be replacement blocks in a file, right? So if we write data block X in file Y, we're just going to go, we conceptually are just replacing that block. Okay? Conceptually just replacing it. We're not going to replace it in the log structure file system. We'll see that in a couple minutes. So what's going to happen now is I write a data block. I don't have to write the whole file or the whole directory. I'm just going to write that one data block. And then when we've made that change, we also have to write the brand new inode. Because the inode is a fixed data structure, so we're going to have to modify the inode. All right? So like access times, things like that. So the inode will be here. The thing that's interesting about this, that is part of what gives it all of its performance, is that this is how it's going to stay on disk. We're not going to replay this. So these logs are going to have data blocks and their associated metadata, the inode, the IMAP, and the data block map, okay, written into each log. All right? The entire disk now is going to be carved up into logs. Okay? And when we write one log, we're done writing that log, and we fill up the we're now going to call it a log in memory, we'll write that to the next open slot on the disk. And the next open slot on the disk, and the next open slot on the disk. Now, a couple of things that show up with this. As I said, when we write the data blocks, we only write the ones that have changed. So that means over time, a file can be spread across many of these logs, can't it? So the inode has to track for this block where is the most recent copy of the block. That's why we need the most recent copy of the inode. Okay? But if we're writing an inode every time we update a data block for a file, that inode can be spread everywhere, can't it? But only one of them is the most recent copy. So all we have to do is track the most recent copy. So this is the way that it works. When we fill up that log, and it's just like this data blocks, inode information, IMAP, etc. The logs are numbered, but we know where the logs are at because all the logs are a fixed size. And our entire disk is spread out that way. So if we're in log 21, we know exactly how to figure out where on the disk log 21 is at. So what we're going to do now, when we write that log to disk, we're going to say, hey, which pieces of meta information, that is inodes and IMAP and data map, okay, have there been any changes in this? Are there any changes in this log? So if you haven't allocated any new inodes, okay, or deleted any inode, deleted any files or directories, then there'll be no change to the IMAP. If you have not allocated more data blocks or deleted more data blocks, then you don't need to store the IMAP. But you do need to store the inode. So the meta information that we need to have about the meta information, we need some place to say where is the most recent copy of inode X. Which log? Then in these logs, it'll have a header on it that says, I contain the following inodes, and this is where they're located inside the log. So we can go directly to them. Okay. Now, once we have the data, the inode in memory, we don't have to go back to the inode for reading. Okay, it's in memory. We don't have to go off and find it on disk. But if we're doing a pure read, yes, we're going to have to go get that meta information, figure out where the log is for the most recent copy of the inode, and then go through, for all the blocks that are in it, we might have to read a bunch of different logs in order to get the data. Okay, so reads are still random, but we don't care why. Well, but why is it fast? It's fast. It's fast, and because it's fast, it turns out we don't need to care about reads.
You just need to do it once you put it in memory.
Yeah, we do them almost never. We do the minimum. We do not read very often. We read the first time we touch that data block. Okay. The disk, remember, is write dominated because of what? Yeah, the buffer cache and the fact that we have big memories. So the buffer cache is huge. So once we tend to bring a page, when we go to bring a page into memory, there is typically, that is probably 99% of the time or better, there's a free page frame. And we don't have to eject pages to get free page frames with the size of our buffer caches today. So, our disks are write dominated. We're going to optimize those by making them contiguous. That is one seek, and then we just write contiguously across the disk, no scans. Our head moves are just to the next track, which is the minimum movement we can have. All right. But then we have to update the metadata of the metadata. So does anybody know what we call the areas where we store the metadata? checkpoint regions, right? So what we're going to do is after every time we write a log to disk, what we're going to do is say what meta information is stored in this log, and then we'll go to the checkpoint region and update it. You guys ever heard of a disk crash? What could conceivably go wrong with this? What if you're in the middle of updating that checkpoint region using a transaction so that, we kind of hide that sometimes it's in an inconsistent state? And what if we crash and leave that checkpoint region in kind of a garbage state? Would that be useful? How do you think we're going to fix this? Why build one when you can build two for only twice the price? We're going to have two checkpoint regions. And logically, we say they're at either end of the disk. They're just at least two. And the at least two does something for us really rather interesting. If we crash before we updated the current checkpoint region, we have the previous checkpoint region. Because we strictly alternate. Okay, let's say the checkpoint regions are 0 and 1. Then if we've just finished writing to checkpoint 0, checkpoint region 0, we'll go to CR1 for the next update, and then back. So we'll only ever be one checkpoint region out of date for the most current data. So if we get a corrupted checkpoint region, all we do is go back to the old checkpoint region, the previous one. And that's the equivalent of losing a log, which is equivalent of crashing with the buffer cache, right? Go ahead and take a message. I just been getting these scam calls. They're starting to call my students' phones too now. Just to scam me. I know it. But I'm not paranoid. Now, these checkpoint regions with the strict alternation give us what it turns out to be is faster crash recovery than the journaling file system. The journaling file system's a few hundred milliseconds, though. It's not that bad. But it turns out that we can do the recovery in the log structure file system in a couple microseconds. So what we're going to do is when we start writing the log, we're going to do the same thing we did with the journal. We're going to indicate, okay, excuse me, let me back up. When we first go to write the log, we have to know where to write it on disk. So the most recent checkpoint region has a pointer for us of which log is currently empty. We can go to that log and start writing. Okay? So we're going to go off, and the first thing we're going to do is say, we're currently writing the log. Okay? So wait, but this information is stored in the checkpoint region. We're going to say, we're currently writing the log. When we finish writing the log, we're going to go back to the checkpoint region, same checkpoint region, and we're going to say, update all the meta information, and then mark the log as written. We don't have to mark it as being played out, because we don't do playout anymore. Okay? So now, we only have one update that's occurring. We mark when we start writing the log and mark when we end, and before we mark that we've ended, we update the metadata. Why don't we mark that we've finished writing that and then write the metadata? It seems to me, saying that it's all on disk is pretty important. So why is it that we take the time to update the metadata before we say that we finished writing the data to disk?
Because you could crash while you're updating metadata, and then you would just be like, it's good. Wait,
Yeah, so what happens is if I say it's good, then that means it made it to the disk good, and now I can go off and start writing to a different checkpoint region, but I don't remember what the previous checkpoint region was. So the only thing I can really do is not mark it as as done until I finish all the work associated with it. Or we have this race condition, if we have a crash, after we mark it as good, but metadata not updated. That can get really, really ugly in terms of recovery.
I think I might have a misunderstanding. But what if you had a crash while you're updating your, like, inodes and data?
Mm-hmm.
So you crash during that point, and you're going to refer to your last checkpoint, which might still have
Last known good checkpoint.
last known good checkpoint.
Yes.
So even if your inodes or data was updated, it would be kind of out of sync. But it
You
would-
could write the complete log, but not have marked the checkpoint region as that log being valid. And if you have a crash, all you can do is lose that log. Okay, because the checkpoint region is not in a good state because it has an operation that has started but has not completed. So if we have a crash in there, that leaves that checkpoint region in an unknown state. So we have to go back to the old checkpoint region and mark and say we pick up where we left off there.
So you would most lose the changes which happened in between.
Yeah, and that's only going to happen while we're writing out the log. And while we're writing out the log, we can't be filling the in-memory log. So all we've lost is one buffer cache worth of data. It's the same risk as the journaling file system. Okay? It's the exact same risk. Okay? Does that make sense? All right? But crash recovery is real fast. We go out, you ask the disk, how many checkpoint regions do you have? We're just going to assume 2. Okay, I'll go read the 2 checkpoint regions. Whichever one has, and when we mark them as completed, we're going to somehow timestamp that. There's different ways to timestamp, including a counter. And a counter that just starts at 0 and just keeps increasing is the same as a timestamp, because the one with the higher number is the most recent. We don't care about the exact time, we just care which one is the most recent.